In most parts of the world, especially where diamond-bearing pipes are no longer active, the average person steps over fortune without a second glance. Riverbanks, especially the gravel bars that appear during seasonal lows, often hold clues to something far more valuable than gold. The common mistake is assuming that the absence of visible crystals means the area is barren. But diamonds rarely announce themselves. What gives them away is what surrounds them. In downstream zones of ancient or eroded kimberlite or lamproite pipes, diamonds can travel far from their volcanic origin, sometimes over 100 kilometers. The evidence doesn't come as a sparkling gem perched in plain view. Instead, it's a suite of dense, dark, seemingly dull minerals. Pyrope garnet with a deep purplish hue, metallic black ilmenite, and blocky chromite fragments. These minerals travel with diamonds because they originate from the same ultramafic source rock. Where these cluster in river sediments, diamond probability spikes. Gravel bars form during rapid flow deceleration, typically on the inside bend of meandering rivers, are prime trap zones. These bars are not just random rock piles, they are density sorters. When water speed drops, heavier minerals fall out first. This sorting concentrates dense indicator minerals and diamonds into tight zones. Even small rivers in regions like southern Africa, parts of Brazil, Siberia, Canada's Northwest Territories, and the U.S. state of Arkansas exhibit this pattern when near ancient pipes. The key is understanding that diamonds are not the starting point, but the potential outcome. First, the field explorer must find what the market calls the pathfinder suite. These are not precious in themselves, but their presence radically shifts the odds. Without them, you're panning blind. With them, you're in territory that warrants real investigation. But here's where most give up. Spotting these indicators requires more than a casual glance. Their luster is submetallic or dull. Their colors, black, red, brown, dark purple, don't jump out. But in a specific light, under magnification, or sorted through a fine sieve, their shapes and densities set them apart. And when they appear in groups, in the right context, the signal can be stronger than spotting a single diamond fragment. What most people discard as just sand and rocks may, under the right flow pattern and geologic background, be the last visible trace of a much older diamond deposit. The question becomes, how do you recognize that first silent signal when it happens? A common pitfall in riverbed prospecting is mistaking glimmer for gem. Sunlight bouncing off wet gravel can produce dozens of false positives in a single glance. Mica flakes, quartz chips, even broken glass. But diamonds reflect light differently, and understanding that subtle difference is the first filter between casual curiosity and credible discovery. Unlike quartz or mica, a diamond's luster is adamantine, meaning it reflects light with a sharp, almost oily brilliance that's unmistakably more intense. In practical terms, this shimmer appears more like a flash than a sparkle. It doesn't flicker, it jolts. A trained eye learns to pick out that tight, high-energy return from the softer, more diffuse gleam of common minerals. But it's not just about light quality, it's about light behavior. Diamonds, due to their high refractive index, often flash white or gray even in multicolored surroundings. They stand out precisely because they fail to match the ambient hue. In contrast, quartz will tend to reflect the colors around it, dulling its impact. In clear water, a diamond fragment may appear unnaturally bright against a brownish sediment background, especially if it's clean and uncoated. But few natural diamonds are. Most are rough, coated, or embedded. So, a more reliable method combines the shimmer test with habit recognition. Diamonds in their rough form rarely look like cut stones. They present as small, greasy-looking, often octahedral or dodecahedral shapes. The trick is to slow down when you see a dense glint that doesn't scatter. Rather than grabbing, observe. Does it hold its brightness under shadow? Does the shape suggest symmetry or crystal habit? Is the surface pitted or oddly smooth? To test it further in the field, a simple hardness check can eliminate most imposters. Quartz scratches at a hardness of 7. If your suspect scratches it cleanly, and you've ruled out common lookalikes like moissanite, you're on firmer ground. Even better, if you carry 6 sandpaper, about hardness 9. A quick swipe can eliminate everything but diamond, corundum, and moissanite. The latter two are common in synthetic jewelry simulants, but extremely rare in river alluvium. Still, shimmer alone isn't enough. The most reliable clues emerge when light behavior matches other physical cues: location, weight, density, and context. For example, if the suspicious glint appears in a heavy mineral concentrate, near magnet-attractive grains, or visible garnet fragments, the odds shift dramatically. The ultimate aim is not just to spot a flash, but to ask, does this shimmer emerge from a context consistent with diamond transport? A real find won't stand alone. It will sit in a pattern. That's why every promising flash must be considered alongside the question, what else is in this pan, and does it belong to the suite? The richest diamond-bearing rivers are not always obvious. Many no longer flow anywhere near a known volcanic pipe. This misalignment has misled generations of prospectors. But it's also the key to untapped discovery. To understand why, you must look backward. Not just a few decades, but millions of years into the paleoflow history of the land. Kimberlite and lamproite pipes, the volcanic conduits that carry diamonds from the mantle, erode over time. Once exposed to the surface, their material gets weathered and broken down, and the dense components, including diamonds and indicator minerals, are carried off by surface water. But that water doesn't follow a static path. Rivers migrate, meander, split, and abandon channels across geological epochs. This means the diamonds you find in today's riverbed might have been released from a source now buried or invisible, and the transport route could have shifted dozens of kilometers. This paleoflow logic underpins serious fluvial diamond exploration. For instance, in southern Africa, the Orange River has transported diamonds from inland pipes across hundreds of kilometers to the Atlantic coast. Similar downstream migration is documented in Canada's Slave Province and parts of Brazil. So what are you looking for in the modern landscape? Start with areas where geophysical surveys or old maps show remnants of ultramafic rock or volcanic breccia, especially if erosion is evident. Next, identify whether any current rivers cut through or near these zones. But just as critical is recognizing terrace deposits, flat, elevated remnants of older riverbeds that no longer carry water. These paleochannels often hold the densest concentrations because they represent ancient trap zones that have gone undisturbed for millennia. Mapping these paths requires a combination of satellite imagery, topographic overlay, and sometimes historical flow data. But on the ground, there are visual signs: abrupt changes in gravel composition, dense mineral lag deposits, or unusually rounded ultramafic fragments. In some cases, a field magnet can help detect magnetite-rich sands that accompany eroded kimberlite fragments. One advanced tactic is to look for counterflow anomalies, where indicator minerals appear upstream or lateral to a known source. These can suggest secondary transport from tributary systems or glacial reworking, depending on the region. For example, in parts of Canada and northern Europe, glacial movement carried diamond-bearing material far from its pipe origin before fluvial action took over. The best finds come when multiple clues converge: a current or paleochannel with heavy mineral traps, evidence of upstream ultramafic erosion, and a concentration of known indicator minerals. These elements form a logic grid that narrows where time and effort should go. Yet the terrain doesn't always cooperate. Rivers bury evidence beneath seasonal sediment loads or shift their energy zones year to year. Recognizing where a diamond may have paused, settling just out of reach in a gravel pocket, means learning to read not just the river, but the memory of the riverbed itself. The biggest secret in fluvial diamond hunting isn't the diamond itself. It's the minerals that travel with it. These indicator minerals are geologic witnesses, immune to market hype and harder to fake than any shiny stone. They're heavier than typical river sands, more resistant to weathering, and chemically tied to the same ultramafic eruptions that brought diamonds to the surface. Yet they're easily dismissed by the untrained eye, mistaken for debris or iron-rich dirt. For indicators dominate the expert's toolkit: pyrope garnet, ilmenite, chromite, and occasionally magnetite. Pyrope garnet, the most iconic, ranges from deep violet to purplish red and has a high density, often over 3.8 g/cm superscript 3. In sunlight, clean grains show internal glow under magnification, unlike the duller red of common almandine garnets. Their angular shape and high fracture resistance keep them intact over long transport distances, which makes them ideal river signals. Ilmenite and chromite are less flashy, but arguably more diagnostic. Ilmenite presents as metallic black or gray grains, sometimes with slight iridescence or a thin weathered coating. It's weakly magnetic and highly dense, over 4.5 g/cm superscript 3. When concentrated in a pan, it forms heavy tails and resists water, washing far more than sand or mica. Chromite, often jet black with a glassy luster, can appear octahedral or nodular and typically clusters with ilmenite in diamondiferous zones. Magnetite, while more common, is context-dependent. Its strong magnetism is useful for sweeping pans or concentrates quickly. If magnetite appears alongside ilmenite or pyrope garnet in a known kimberlite region, that's a major signal. Alone, it may simply reflect regional mafic rocks. To use these indicators effectively, a systematic approach is essential. In the field, you begin with fine sieving, #20 or number 40 mesh, to isolate heavy mineral fractions. A simple rare earth magnet, swept through dry concentrate, removes magnetite and some ilmenite. What remains should be handpicked and examined under 10x to 20x magnification. Key features to spot include garnet's dodecahedral habit, ilmenite's metallic sheen, and chromite's submetallic luster with rounded edges. Color alone isn't enough. Many rivers carry red or black minerals. What matters is how they behave underwater. Heavy indicators move reluctantly, often sitting in low-energy zones or clinging to riffle corners in a sluice. Once you've seen pyrope garnet roll compared to quartz, the difference is unmistakable. This is where field intuition builds. Repetition trains your eye to see the outliers. But indicator minerals have their own traps. In some regions, spinel or zircon can appear in the same zones and mislead those not paying close attention. Zircon in particular is dangerous. It's dense, often brilliant, and can mimic the appearance of valuable signals. Yet zircon lacks the volcanic signature of true pathfinders. It doesn't co-locate with kimberlite-derived minerals and has a higher tendency to fracture into smaller, more irregular grains. Ultimately, the presence of multiple indicators together, especially when magnetically, visually, and contextually consistent, is the strongest argument for diamond potential. One garnet may mean nothing, but garnet plus ilmenite in a heavy concentrate from a known trap zone? That's a message. Ignore it, and you walk away from value. Follow it, and you're one layer closer to proof. When you're miles from a lab, and the river offers only fragments of possibility, grab sampling becomes your most powerful early-stage tactic. The goal isn't to find a diamond immediately. It's to prove the area deserves your time. And that starts by knowing exactly where and how to take samples that mean something. A proper grab sample isn't just scooping sand. It's a focused extraction of sediment from likely trap zones, areas where heavy minerals naturally accumulate due to water dynamics. Inside bends, downstream of large boulders, behind root mats, and at the base of riffles are all prime spots. These areas consistently experience low flow velocity during floods, allowing dense particles like garnet, ilmenite, and possibly diamonds to settle out. The ideal grab sample is about half a liter of material from one tightly defined spot. Avoid mixing from multiple points. That dilutes the signal. Use a small trowel, snuffer bottle, or even a cut-down plastic bottle to scoop directly from the concentrate layer, which often lies just above bedrock or compact clay. If you're working in gravel bars, look for dark, iron-stained lenses or visibly different mineral layers just under the surface wash. Once collected, the sample needs to be reduced. A gold pan is standard, but a fine mesh classifier, #20 or number 40, is essential to remove oversized material. You're not looking for nuggets here. You want to isolate the heavy fine fraction. As you pan, watch how the material behaves. True indicator minerals resist the water's pull, dragging slowly across the pan even as lighter sands rush ahead. If you're down to black sand in under a minute and it still holds weight, you're in a target zone. In the final concentrate, it's common to use a magnet sweep, either handheld or mounted beneath a pan, to remove magnetite. What remains is your potential signal. From here, visual identification with a hand lens can begin, but only after drying. Wet minerals can hide their true luster and make color judgment unreliable. Tag each sample. GPS coordinates, time of day, water level, flow direction, substrate type. These all matter. Even a promising sample means little if you can't relocate or replicate it. A field log or voice memo app can save hours of backtracking. Over time, sample clusters reveal patterns. If pyrope shows up in 3 consecutive points along a bend, while upstream is blank, that's meaningful. Grab sampling doesn't replace full-scale survey work, but it's the first decision gate. A few hours can either eliminate kilometers of false promise or spotlight a stretch that deserves grid testing, sluicing, and eventual lab assays. And here's the advantage many overlook. Because grab sampling is light, cheap, and fast, you can repeat it across dozens of locations in a single trip. Diamonds are rare, but their indicators are not. The faster you isolate those signals in context, the sooner you transition from prospector to data-backed explorer. Even with sharp eyes and careful panning, some of the most critical field distinctions come down to a simple but overlooked sense: how a stone feels in your hand. In the absence of lab equipment, your own tactile perception of density becomes an early and surprisingly reliable gatekeeper. It's not foolproof, but in practiced hands, weight in hand can instantly rule out dozens of common distractions and spotlight a possible diamond path. The density, or more precisely, specific gravity, of a material determines how heavy it feels for its size. Most typical river pebbles, like quartz or feldspar, have a specific gravity between 2.6 and 2.8. Diamonds sit at about 3.52, which doesn't sound like a huge jump, until you're holding 2 stones of equal size and one drops harder into your palm. Pyrope garnet can exceed 3.8. Ilmenite ranges from 4.5 to over 5.0, and chromite is heavier still. These differences are subtle, but unmistakable when you know what to compare. The best way to train this sense is side-by-side comparison. Pick up a quartz pebble the size of a pea. Then handle a garnet of similar volume. You'll notice it instantly. Now translate that into the pan. If something small resists movement underwater and drops with an unexpected thud onto a metal or ceramic plate, that's a cue to investigate further. In the field, density clues show up even before you pick anything up. As you swirl your pan, denser minerals hug the bottom. They travel slowly across the pan's surface, defying the water's flow. They cluster in the last corner while lighter minerals wash away. This behavior, sinking fast, resisting momentum, dragging late, is a telltale of heavies. If your final pan always ends with only mica and quartz, you're not in a target zone. But if every second or third pan leaves a stubborn tail of black, red, or metallic grains, weight is speaking. To make this more systematic, some field teams carry small digital scales and volume flasks for crude specific gravity tests. A simple method. Weigh the dry sample, then weigh it submerged in water using a mesh sling or fine sieve. The difference gives you a rough SG reading. While not lab grade, this technique is surprisingly effective at separating quartz, SG 2.65, from garnet, SG 3.8, or ilmenite, SG 4.7. But many don't need a scale. They just need practice. One trick used by artisanal miners is the drop sound test. Placing a stone on a metal plate and listening to the note it strikes. Denser stones drop faster and hit harder, often with a sharper ping. It's primitive, but in experienced hands, useful. Mistakes happen when visual cues override tactile ones. A bright, clear crystal may dazzle in the pan, but if it lifts like a feather, it's likely quartz or feldspar. Conversely, a dark, unassuming grain that sinks like a lead shot may be the first real sign of kimberlite-derived minerals in your sample. In the end, the river doesn't hide its story. It just tells it in weight, not words. And if you learn to listen, your hand becomes the first lab instrument in a process that could lead to something rare and lasting. One of the most efficient tools in your diamond scouting kit isn't high-tech. It's a magnet. Specifically, a strong rare earth, neodymium, magnet, small enough to fit in your pocket, but powerful enough to move black sands with a twitch. In the right hands, it turns a half hour of guesswork into 5 seconds of signal clarity. Because many diamond indicator minerals respond to magnetism, and many imposters do not. This simple field test instantly sharpens your sample's meaning. Start with dry concentrate. Wet sands cling and obscure magnet movement. So drying your pan tailings on a flat rock or tray is a key prep step. Once dry, drag your magnet slowly across the sample or hold it just above the surface and observe what reacts. If particles leap upward or shift distinctly toward the magnet, you're seeing magnetic responsiveness, most likely from magnetite and possibly from ilmenite. Magnetite is strongly magnetic and common across many geologic settings, so it's not diagnostic on its own, but its presence in concentrated pockets, especially when accompanied by other indicators like garnet or chromite, can reinforce a kimberlitic source context. Ilmenite is the more subtle but telling response. It's only weakly magnetic, especially when weathered. However, a neodymium magnet can still pull it slightly or cause it to drift with motion. That gentle drag is what separates real pathfinders from common black sands. Sweep techniques vary. Some prospectors mount a magnet inside a small plastic container, allowing particles to collect without contaminating the magnet. Others use a Ziploc bag around the magnet, then invert and tap it to release the collected material. This method speeds up multi-sample sorting and helps isolate magnetically active grains for microscope inspection. The real payoff comes when magnetism cross-checks with density and luster. If a grain responds to a magnet, sinks heavily in the pan, and reflects with submetallic or metallic sheen, it becomes a candidate for closer inspection. When that grain also occurs alongside a cluster of non-magnetic garnets or opaque spinels, the context grows more compelling. On the flip side, magnetic screening also helps eliminate distractions. Many visually attractive grains, zircon, tourmaline quartz fragments, don't respond to magnets and are much lighter. If a sample has no magnetic response and no heavy retention in the pan, it likely lacks indicator minerals altogether. This is where the magnet saves time. You move on sooner from zones that can't pay off. However, the danger lies in assuming magnetic means valuable. Plenty of magnetite-rich areas have zero diamond potential. It's the co-occurrence that counts. Ilmenite with chromite, or magnetite with garnet clusters, in a trap zone near suspected pipe erosion. That's the package. And while not all ilmenite is magnetic, enough of it is to make the magnet sweep a worthwhile first-pass test. In sum, the magnet isn't for finding diamonds, it's for finding the friends diamonds travel with. And when used systematically across your grid, it builds a mineral fingerprint that can trace flow patterns and point to origin zones upstream. When it comes to field verification, most casual prospectors underestimate the utility of thermal conductivity testers. Originally designed for jewelers to distinguish diamonds from imitations, these compact tools, often no bigger than a pen, can, under the right conditions, give rapid clarity in the middle of nowhere. And while they won't confirm a diamond on their own, they can eliminate 90% of lookalikes in seconds, saving time and samples for what truly matters. Thermal conductivity testers work by placing a small probe against the stone's surface and measuring how quickly heat dissipates into it. Diamonds conduct heat exceptionally well, one of the highest rates of any natural material. Most imposters, including quartz, glass, and zircon, do not. So when the tester tip touches a diamond, the device reacts instantly, usually with a beep or a needle jump to a diamond zone. In the field, however, conditions matter. Moisture, dirt, or grease on the stone can throw off readings. That's why the first step is cleaning. A small spray bottle of distilled water and a microfiber cloth or toothbrush should be part of your kit. The stone must be dry and free of oils to give a reliable reading. Temperature is also a factor. Thermal testers assume room temperature baselines. If you're in extreme heat or cold, results may skew. So keep the device in your inner pocket or shaded pouch to stabilize its electronics. Some modern units auto-adjust for ambient temperature, but all require a steady hand. Press the probe lightly against a flat facet or polished face. Rough stones can produce inconsistent readings if the tip doesn't make full contact. Still, when used on dry, clean surfaces, the tester's results are decisive. A true diamond will trigger the device immediately. Moissanite, its primary competitor in the fake world, can also trigger thermal testers, which is why higher-end units now include electrical conductivity probes as well. That's critical in the field. If your stone passes the thermal test, your next question must be whether it conducts electricity. Moissanite typically does. Diamond does not. Field kits that include both thermal and electrical testers, compact, battery-powered units, offer the best mobile solution. They can't replace lab spectroscopy or SG testing, but they offer something labs can't: immediate triage. In remote areas, being able to test 20 stones and eliminate 18 outright allows you to focus on the 2 that might be worth cutting, certifying, or mapping. The other advantage? Chain of custody. If you field test a stone and it passes both thermal and electrical criteria, you now have reason to document its GPS location, note associated indicators, and log environmental context. That's the beginning of a provenance trail, a crucial factor if the stone turns out to be authentic and significant. But be warned, some cubic zirconia imitations now include metal foil backing or high-index coatings that can confuse cheap testers. That's why context matters. A loose stone found in city soil may just be lost jewelry, but a rough crystal in a trap zone, alongside pyrope garnets and ilmenite, that passes thermal and fails electrical? That's not a trinket. That's a serious lead. It was supposed to be a routine verification run, an alluvial site flagged by previous sampling for elevated garnet and ilmenite content. The pan samples were textbook: heavy black sands, clusters of wine-red garnet fragments, and unusually dense concentrate tails that resisted even aggressive sluicing. On paper, everything aligned with classic fluvial diamond signatures. The field crew, working under contract for a mid-tier exploration firm, began grid mapping with confidence. But they missed one signal that would later redefine the site's true nature. The trouble began with repeat positives. Nearly every test pit along a 200-meter stretch yielded a consistent suite. Sharp-edged garnets, dense black grains, and even a few transparent octahedral crystals. Under loop, the shapes were right. Under pan, the behavior was heavy. Under magnet, some grains resisted, others responded faintly. The thermal tester pinged on 3 different crystals. Electrically inert, hard enough to scratch quartz, and visually convincing. This was what a field diamond target looked like. Samples were tagged, cataloged, and shipped for lab analysis. Then came the report. No diamonds present. Not even fragments. What the team had uncovered wasn't diamond-rich material. It was a zircon-heavy alluvial fan with high accessory mineral content. And the culprit was a misread suite of high-density, non-kimberlitic indicators sourced from a nearby pegmatite intrusion that had weathered into the system. Zircon, especially in its clean, transparent form, can mimic diamond behavior in several ways. It has a high specific gravity, around 4.6, responds similarly under pan movement, and often crystallizes in prismatic or pseudo-octahedral habits. In dry field conditions, a high-quality zircon crystal can even cause a low-end thermal tester to register a weak positive. Add to that its occasional placement near magnetite streaks or garnet-rich mica schists, and the illusion becomes hard to break without proper lab confirmation. The crew retraced their steps and discovered the critical miss. Contextual mineral association. While pyrope garnets were present, their chemistry under spectroscopy showed they were more closely related to metamorphic almandine types, not the chromium-bearing garnets tied to kimberlite. The ilmenite wasn't titanium-rich, but derived from weathered magnetite ilmenite solid solutions, common in pegmatitic zones. And the transparent crystals? High-grade zircon fragments, chipped from upstream orthogneiss exposures. This kind of false positive isn't rare. It highlights a field truth that haunts even seasoned teams. Real indicators must be chemically right, not just physically similar. Surface-level attributes, weight, luster, magnetism, shape, only tell part of the story. Without cross-verifying with known kimberlitic chemistry or origin alignment, a pan full of hopefuls can quickly turn to a lesson in humility. What saved the operation wasn't the equipment. It was the team's decision to hold samples for lab confirmation before escalating to bulk testing. Had they proceeded with heavy trenching or licensing steps, the cost would have risen exponentially for zero return. Instead, the experience recalibrated their process. Higher scrutiny on garnet chemistry, more aggressive zoning on indicator clusters, and tighter provenance filtering for transparent grains. And most importantly, it sharpened their recognition of a key rule. When everything looks right, but the data says no, there's usually a deeper story buried beneath the surface. Sometimes, the false trail is the clue that leads to the real one. The difference between a lucky find and a credible discovery comes down to repeatability. Anyone can stumble on a garnet-rich pocket or a promising shimmer in a single pan. But professionals don't stake claims or reputations on isolated hits. Instead, they impose a structure on the chaos of the river. The grid. It's not glamorous, but it's the backbone of every serious fluvial diamond exploration project. The principle is simple. Divide the search zone into a uniform grid, typically using 5 by 5 or 10 by 10 meter cells depending on terrain, and sample each cell independently under identical conditions. This removes subjective bias. No chasing glitter. No skipping barren-looking spots. The data, not the hunch, guides decisions. Each grid cell is tested with a consistent method. Usually 1 to 2 liters of sediment collected from the same stratigraphic layer, often just above bedrock or from trapped gravel behind natural riffles. The material is sieved to uniform grain size, reduced via panning or sluicing, and then examined for indicator mineral content. Every sample is labeled with exact coordinates, elevation, water flow direction, and a brief environmental note: vegetation, substrate, flood debris, or erosion signs. What makes the grid powerful isn't any one sample. It's the pattern that emerges. When 3 adjacent cells show no indicators, but the fourth holds dense ilmenite and pyrope fragments, a vector appears. That's a transport clue. It might suggest a back-eddy trap zone, or point to an upstream pipe. If the pattern repeats across different water levels or seasons, it builds a case for continuity, meaning material isn't just caught by chance, but reflects persistent flow sorting. Repeatability also gives you control against false positives. If a zircon cluster lights up one pan, but never appears again, it's a random event. But if garnet plus ilmenite pairs show up in multiple cells with correlated density and magnetism, the signal is real. And when that pattern aligns with topographic traps, meander bends, bedrock fissures, or paleochannel remnants, you have not just data, but a narrative of how diamonds could have moved and settled. Some grids extend vertically, not just laterally. In deeper gravel systems or terrace deposits, test pits or auger samples capture vertical changes in mineral concentration. Often, indicator density peaks in a narrow pay zone, sometimes only 10 to 30 centimeters thick, just above clay or bedrock. Missing that layer by sampling too shallow can erase the signal entirely. Professionals often mark grid cells with biodegradable flagging, log every reading digitally, and return to hot zones with denser sampling. A single anomaly might lead to a 1 by 1 meter high-resolution mini-grid, with each quadrant sampled independently to track mineral distribution across inches. Why does all this matter? Because real diamonds are rare. Even in productive zones, you might find only 1 to 3 diamonds per 100 tons of gravel. But the indicators, if read correctly, allow for a predictive model. That's how mines are found, not with a flash in the pan, but with a mosaic of mineral behavior across time, flow, and structure. In practice, the grid is your lens into the river's hidden memory. And once a repeatable pattern is logged and verified, the next move isn't more panning. It's deeper excavation, bulk sampling, or lab prep. The data says where to go. The grid makes that data possible. There's a moment in every serious fluvial exploration effort when the tools must shift from pan to pen, or more precisely, from recovery to documentation. Knowing when to make that pivot is what separates a recreational prospector from a methodical field geologist. Because panning can only show you what's there now. Coordinates preserve what's there systematically. That distinction is critical when you're chasing a mineral as elusive and low-frequency as diamond. The rule of thumb is simple. When 3 or more key indicators appear in the same location under repeat sampling, you stop treating it like an anomaly and start treating it like data. For fluvial diamonds, that typically means finding at least 2 of the following in a single pan: pyrope garnet, ilmenite, chromite, or a dense, angular, translucent grain that passes hardness and thermal tests. If these indicators persist across more than one pan, particularly within a 10-meter radius, it's time to log. Logging doesn't mean sketching in a notebook and moving on. It means exact GPS coordinates, preferably in decimal degrees for mapping, backed by environmental metadata. Water level, sediment depth, grain composition, flow velocity, and substrate type. Even ephemeral features matter. Flood debris lines, recent bank collapses, or new sandbars may indicate fresh exposure zones or sediment traps that won't exist next season. Modern teams use mobile GIS apps with offline base maps to mark and export sample points in real time. But even a handheld GPS unit and a waterproof field book are enough. The goal is consistency. Every location where indicators show up gets logged, numbered, and assigned a sample ID. If the concentrate is saved, which it should be, it gets bagged with that ID and stored for cross-reference with later lab or grid work. One missed detail here can collapse the chain of evidence. Imagine a field site where promising minerals were found in March, but the note said gravel bar near bend. 6 months later, the river shifts, the bar's gone, and so is the exact hit zone. Without coordinates, the opportunity vanishes. Field teams also note what isn't there. Blank zones, cells with zero heavies, are just as important as hot spots. Together they form contrast, helping isolate trap zones, back eddies, and paleochannel remnants. A scatter of garnets along one bend, but none on the opposite bank, could indicate directional transport or secondary sorting, a clue toward pipe location or erosion path. Documentation also opens the door to legal security. In many jurisdictions, logging coordinates is step one toward formal mineral rights exploration applications. Without a record, you can't protect your find. But with it, you build provenance, demonstrate due diligence, and can return for bulk sampling with credibility. There's a practical limit to panning. No matter how good your eye or technique, a single pan can only hold so much sediment. And diamonds don't follow the rules of frequency like gold. What matters is pattern. Once you see a pattern forming, the time for individual tests ends. You log, you map, you scale. If there's one mineral that consistently outsmarts even experienced field teams, it's moissanite. On the surface, and under many standard tests, it looks, feels, and even behaves like diamond. It shares the octahedral habit. It's nearly as hard. It passes most thermal conductivity testers, and unless you're using the right tools or asking the right question, it can pass through a field operation undetected, earning logging priority and lab fees it doesn't deserve. Originally discovered in meteorites and later synthesized for industrial use, moissanite has since entered river systems as both an industrial contaminant and a rare natural find. Its visual cues are nearly identical to diamond. Colorless, sharp edges, high brilliance. Under loop, it often shows the same greasy surface appearance as uncut diamond. Even its density, about 3.22 g/cm superscript 3, is close enough to diamond's 3.52 that, weight in hand, offers little help. Thermal testers, which most field teams rely on for fast triage, consistently misidentify moissanite as diamond. That's because moissanite is nearly as thermally conductive as diamond, enough to trigger a positive on 90% of handheld units. So when you're in the field, in a trap zone, panning concentrate, and a transparent octahedral crystal appears and passes the thermal test, your instinct is to flag it. This is where moissanite creates the most damage, not just as a false lead, but as a data disruptor. It forces you to question every positive. If one crystal passed, how many others might be clever fakes? The cost isn't just one misread. It's time lost, grid cells misprioritized, and lab hours wasted. The solution is surprisingly simple, but often overlooked. Electrical conductivity testing. Moissanite conducts electricity. Diamond does not. And there are field testers, some even under $200, that combine both probes into a single unit. The moment a stone passes thermal, but also shows electrical response, you know you're dealing with moissanite or another synthetic. There's also a loop test, though it takes a practiced eye. Facet doubling. Moissanite is doubly refractive. Diamond is singly refractive. When you look closely at a faceted or partially formed moissanite crystal, you may notice a doubling of facet edges, like a ghost image beside the real one. This doubling doesn't occur in diamonds, and even in rough stones, it sometimes shows along sharp edges or through transparent zones. In field situations where no electrical tester is available, this optical clue becomes the only fallback. Under angled light, rotate the crystal slowly and look for split reflections or double lines along internal fractures. If seen, it's enough to downgrade the sample pending lab verification. Moissanite in rivers is rare, but synthetic debris can travel surprising distances. Especially in systems near industrial sites, cut-stone shops, or historic placer regions. And with lab-grown moissanite increasingly used in low-cost jewelry, even lost or discarded pieces can contaminate a concentrate. When governments, exploration companies, or academic institutions hunt for fluvial diamonds, they don't chase glints in a pan. They chase probability across terrain. This means deploying systematic, staged methodologies backed by decades of data, with each step designed to eliminate chance and confirm origin. These protocols, developed and refined through operations in Canada's Slave Province, Namibia's Orange River System, Brazil's Mato Grosso, and Australia's Ellendale, represent the gold standard for fluvial diamond reconnaissance. It starts with regional screening, not sampling. High-resolution satellite imagery and digital elevation models identify paleochannels, terrace remnants, inside bends, and floodplains with the hydraulic conditions necessary to trap heavy minerals. Overlay maps of known kimberlite or lamproite intrusions further refine the focus area. Even if those pipes are long eroded or deeply buried, their erosion paths can be reconstructed with paleogeographic models. Once a candidate drainage is identified, reconnaissance sampling begins. Not for diamonds, but for indicator minerals. Bulk sediment, typically 20 to 40 kilograms per site, is collected from well-defined trap zones, often near bedrock or in deeper channel cuts. These samples are bagged, tagged, and transported to processing stations, often remote, mobile field labs, where heavy mineral concentrates are separated by gravity, jigging, spirals, or dense media separators. The resulting concentrates undergo magnetic separation, followed by visual picking under binocular microscope. Each grain of pyrope, chromite, ilmenite, or spinel is isolated and chemically tested. Garnets, for instance, are analyzed for Cr2O3 content. Only those within the G9 or G10 chemical range, indicative of deep mantle origin, are retained as true indicators. Ilmenite is tested for TO2 enrichment and trace elements like magnesium and chromium. The protocol demands grain-by-grain documentation. Each indicator is plotted, labeled by grain count, type, chemistry, and sample location. These data points form vector maps that suggest source direction. If multiple drainages show increasing indicator density toward a common apex, the area between them becomes the primary exploration focus. Diamonds, if recovered at this stage, are bonuses, but not yet proof. Most protocols require at least 2 microdiamonds, typically less than 0.5 millimeters, in proximity to geochemically confirmed indicators before a site progresses. These microdiamonds are extracted via caustic fusion, a chemical digestion process that dissolves host rock but leaves diamond intact. It's destructive, expensive, and only used when preliminary indicators justify the cost. Only after a site yields both indicators and diamonds under lab conditions does the protocol shift to bulk testing. Here, excavators collect tons of gravel, sometimes 100 to 200 tons, from the most promising zones. Mobile plants then wash and screen this material, with final concentrates subjected to hand sorting and caustic testing for diamond recovery. The presence, size, and grade of recovered diamonds determine economic viability. Throughout, rigorous chain of custody is maintained. Every sample is traceable, GPS-locked, time-stamped, and backed by procedural logs. This is not for show. It protects against fraud, data loss, and contamination. A single mislabeled bag can collapse months of work. What separates these protocols from casual prospecting is not just scale, it's discipline. Every test has a threshold. Every positive must be repeatable. Every grain must point somewhere. And if the data doesn't converge, the site is closed. No wishful thinking, no sunk cost fallacy. This standard of work, defined by programs like Canada's Northwest Territories Geological Survey or Botswana's Department of Geological Survey, has led to some of the world's most valuable fluvial diamond finds. They did not happen by luck. They happened by protocol. One of the hardest lessons in alluvial diamond exploration is this: not all rivers are equal, and not all terrains can deliver. Even with perfect technique and cutting-edge gear, the geology must be right, or nothing else matters. That's why knowing where fluvial diamonds don't occur is just as important as knowing where they do. It saves months of wasted effort and keeps your focus on the zones that can pay off. First, the source. Fluvial diamonds derive from the erosion of primary deposits, typically kimberlite or, less commonly, lamproite pipes. These ultramafic volcanic rocks formed deep in the Earth's mantle and erupted explosively, bringing diamonds to the surface. But over millions of years, erosion carries the diamonds downstream, sometimes hundreds of kilometers. If a river doesn't intersect, crosscut, or lie downstream from such a pipe, known or suspected, then no amount of panning will change its potential. Regions known for productive fluvial systems share a common trait: proximity to eroded pipes and favorable transport dynamics. In southern Africa, the Orange River carried diamonds from inland kimberlites to the Atlantic coast. In Brazil, the Coromandel and Jequitinhonha rivers flow through weathered terrains rich in both primary and secondary sources. Canada's North Slave region shows similar patterns, where retreating glaciers and post-glacial rivers distributed kimberlite-derived material across vast areas. What makes these rivers work is gradient, substrate, and trap structure. The river must have had enough energy to move dense minerals, but also the right bends, bar formations, and bedrock fissures to trap them. Steep, fast rivers often transport diamonds too far, bypassing trapping zones. Shallow, meandering streams, especially those with irregular bedrock or deep gravel benches, offer better retention. Paleochannels, old river courses now buried or dry, can also hold diamonds, often in concentrations higher than active streams. But in the wrong geology, even perfect-looking trap zones mean nothing. Granite and metamorphic terrains without ultramafic pipes rarely produce diamonds, even when garnet, magnetite, or heavy sands are abundant. Similarly, quartzite-rich regions may yield shiny fragments and mimic mineral sweets, but they typically lack the deep mantle conditions necessary to form diamonds. Many pegmatitic zones produce zircon, tourmaline, and even synthetic contaminants, but never true fluvial diamonds. Coastal zones with marine reworking can also mislead. Beaches in some regions may show diamond-like particles eroded from offshore materials or carried by longshore drift. Yet without a proximal fluvial or glacial feeder system tied to a known source, these are usually isolated anomalies, not productive leads. There's also the issue of sediment load and concealment. Some rivers flow over deep alluvium, meters of soft, shifting silt and sand. Even if diamonds are present, they may be buried under decades of deposition, inaccessible without heavy machinery. In such zones, trenching or auger sampling becomes necessary, increasing cost and complexity. Mapping tools help filter viable terrain. Satellite multispectral imagery, geologic overlays, and geophysical magnetic surveys can identify ultramafic trends, ancient flow patterns, and likely erosion corridors. But ultimately, ground truth rules. A river that crosses a mapped kimberlite belt shows heavy mineral concentration and yields repeatable indicator minerals. That's a field worth logging. In contrast, a river flowing through sedimentary basins with low energy profiles and no upstream volcanic history? It may dazzle with false signals, but it will never deliver. And yet, within favorable zones, a single bend, bench, or terrace could hold diamonds missed for decades. Not because they weren't there, but because no one applied the terrain filter correctly. In diamond exploration, pyrope garnet often steals the spotlight. Its deep color, distinct habit, and mantle-derived chemistry make it the classic indicator mineral. But the mineral that often proves a diamond-bearing environment, quietly, repeatedly, and with greater reliability, is ilmenite. Found in dense, submetallic grains ranging from bluish-black to iron-gray, ilmenite doesn't just confirm kimberlite erosion. It often outlines the diamond path more precisely than any other indicator. The reason is simple. Ilmenite is more abundant and more durable during transport. While garnets can fracture or chemically alter in acidic conditions, ilmenite holds up in a broader range of environments, allowing it to persist farther downstream from source. In fact, some diamond-bearing rivers in Angola and Russia show ilmenite concentrations extending dozens of kilometers beyond where garnets vanish entirely. Ilmenite's density, typically between 4.5 and 5.0 g/cm superscript 3, means it responds predictably during panning. It settles early, concentrates into sharp black tails, and resists flushing. But not all black grains in a pan are ilmenite. Distinguishing it from magnetite, chromite, or even hematite-rich material requires attention to magnetism and luster. Ilmenite is weakly magnetic at best. Magnetite leaps to the magnet. Under bright light, ilmenite shows a slightly metallic sheen. Not quite mirror-like, but more than dull. Its surfaces often show slight blue or gray tints when freshly fractured. The field trick? Use a rare earth magnet to pull out the magnetite. Then observe what stays behind and still feels heavy. Those residual grains, if shiny, rounded but dense and non-magnetic, are likely ilmenite. In promising zones, these clusters are often your first and strongest case for upstream kimberlite. But to move from clue to confirmation, chemical analysis matters. Not all ilmenite comes from diamondiferous sources. Only ilmenite with specific geochemical signatures, high titanium content, TO2 greater than 45%, and trace amounts of magnesium and chromium, is associated with deep mantle derivation. In field practice, this means that bulk samples yielding high ilmenite counts should be prioritized for lab-based microprobe analysis. The presence of multiple grains within that target chemistry is often enough to justify further grid testing or trenching. Another key role ilmenite plays is in provenance modeling. Because it weathers more slowly and disperses widely, its distribution can show the direction and range of transport from the eroded pipe. In several Canadian and Indian survey projects, ilmenite concentrations mapped across stream networks allowed reverse tracing back to previously unrecognized pipes. This mineral vectoring technique is especially useful in regions where erosion is advanced and traditional pipe expressions are long gone. Perhaps most important for field operations, ilmenite appears in clusters. A single grain might be noise, but 5 or 10 grains in a 10 by 10 meter zone, especially when aligned with garnet, chromite, or heavy tailing, signals a consistent erosional source. It's in these clusters, often overlooked or misidentified, that the real story begins. So when the pan doesn't glitter and garnets are sparse, don't walk away. Drop your magnet. Scan the residue. If ilmenite holds, you're not out of the game. You may be closer than anyone else has ever gotten.